Hi, I'm happy to welcome you to my YouTube channel. Today we will be talking about Karpenter, an open source Kubernetes cluster autoscaler. Kubernetes autoscaling is a crucial feature that allows your Kubernetes clusters to dynamically adjust their capacity based on workload demands. Autoscaling ensures that your applications have the necessary resources to handle varying levels of traffic overload without manual intervention. It enables you to optimize resource utilization, improve application performance, and save costs by automatically scaling the cluster up or down as needed. So, let's quickly explore the various ways we can achieve Kubernetes scaling. There are three main concepts, and we'll take a closer look at each of them. In the horizontal pod autoscaling, or HPA, you scale or add more numbers of pods based on the resource metrics. So it's pod level scaling. You simply start adding more and more number of pods as your demand increases, and if your demand decreases, you simply automatically stop the pods to free the resources. So you scale out and scale in as per your need. With vertical scaling, as it suggests adding capacity to the same resource. So the Kubernetes VPA automatically adjusts the CPU and memory reservation for your pods to help right-size your application. Finally, let's talk about the Kubernetes cluster autoscaler, a popular solution for cluster autoscaling. Its primary function is to automatically adjust the number of nodes in your Kubernetes cluster. This ensures that your pods can be scheduled without resource wastage, even in scenarios where pods fail or need to be rescheduled to other nodes. The Kubernetes cluster autoscaler operates by monitoring the cluster for two key conditions. Pods that have failed to schedule due to insufficient resources, and nodes that are underutilized. When it detects these conditions, it simulates the addition or removal of nodes based on the workload demands before actually applying the necessary changes to your cluster. For users running their Kubernetes clusters on AWS, the AWS Cloud Provider implementation within the cluster autoscaler controls the desired replicas field of the EC2 autoscaling group. EC2 autoscaling group is a feature of AWS that allows for easy management of instances with dynamic scaling capabilities. Cluster autoscaler leverage this feature to handle the scaling of the Kubernetes nodes on AWS. By utilizing the Kubernetes cluster autoscaler, you can ensure that your cluster efficiently scaled based on the actual demand from your running pods, leading to improved resource utilization and cost effectiveness. It simplifies the process of managing the cluster's capacity, providing a more dynamic and automated approach to scaling infrastructure in response to changing workload patterns. Autoscaling works in conjunction with horizontal pod autoscaler, HPA. The HPA dynamically adjusts the number of replicas for a deployment or application based on the current CPU or other defined metrics. When the CPU load increases, HPA creates new replicas, potentially leading to insufficient resources in the cluster. To address this, the cluster autoscaler comes into play. If there aren't enough resources to accommodate the new pods created by HPA, the cluster autoscaler will launch additional nodes, ensuring that the new pods have space to run. On the other hand, when the CPU load decreases, HPA will scale down the number of replicas, resulting in some nodes becoming underutilized or even empty. In such cases, the cluster autoscaler will automatically terminate these unneeded nodes, optimizing resource utilization and cost effectiveness. Cluster autoscaler relies on the concept of node groups and EC2 autoscaling groups to manage the cluster's capacity. It assumes that the instance types within a given group are identical. However, if you want to use a node group with mixed instance types, you need to ensure that each type has roughly the same amount of CPU and memory resources. This is important to avoid resource wastage or insufficiency during scale-up events. Supporting different instance types requires multiple node groups. Additionally, it's recommended that each node group should span only one availability zone. The original design of Cluster Autoscaler didn't have the inherent flexibility to handle a large number of instance types across multiple availability zones. It used to load the entire cluster state, including nodes, pods, and node groups, into memory. This approach became complicated and cumbersome, especially when dealing with numerous node groups. Additionally, the time taken for the cluster autoscaler to scale your capacity could be up to 5 minutes, which can have a significant impact in use cases where rapid capacity scaling is critical. The delay may affect the responsiveness of the cluster to changing workloads, potentially impacting end-user experiences and failing to meet customer commitments. As a result, some AWS customers tend to over-provision resources to ensure a consistent end-user experience. Over-provisioning by 20 to 25% is not uncommon in some cases, which can lead to high infrastructure costs and underutilized resources. In use cases like machine learning or batch workloads, quick experimentation is essential. Having to configure node groups and obtain additional resources can slow down the pace of innovation. To address these challenges and improve cluster utilization and efficiency, tools like Karpenter were developed. Karpenter is an open-source, flexible, and high-performance Kubernetes cluster autoscaler that improves your application's ability and cluster efficiency. It launches right-sized compute resources, such as Amazon EC2 instances in our case, in response to changing application load in under a minute. By integrating Kubernetes with AWS, Karpenter provisions just-in-time compute resources that precisely meet your workload requirements. Although AWS is the first cloud provider supported by Karpenter, it's designed to be vendor-neutral. Karpenter works in tandem with the Kubernetes scheduler by observing incoming pods over the lifetime of your cluster. When there is enough capacity in the cluster, the Kubernetes scheduler places incoming pods as usual. However, if pods cannot be scheduled using the existing cluster capacity, Karpenter bypasses the Kubernetes scheduler and directly works with your provider's compute service, like Amazon EC2, to launch the minimal compute resources needed to feed those pending pods. Karpenter also binds those pods on the nodes it provisions. As pods are removed or rescheduled to other nodes, Karpenter looks for opportunities to terminate underutilized nodes as well. Running fewer, larger nodes in your cluster reduces the overhead for daemon sets and system components and provides more opportunities for efficient resource packing. The central concept in Karpenter revolves around provisioners, which are managed using Kubernetes custom resources, a modern and standardized approach for writing controllers. A provisioner defines how Karpenter handles unscheduled pods and expired nodes in a cluster. While the provisioner comes with smart defaults, it is fully configurable, allowing customization of instance type selection, launch template generation, subnet security groups, and more. In the context of Karpenter usage, there are typically two roles: the cluster administrator, and the application developer. The cluster administrator installs and updates Karpenter and defines the provisioners to segment the infrastructure based on specific needs. Provisioners can be configured based on various criteria such as purchase options, capacity type, instance types, availability zones, and more. On the other hand, the application developer deploys the pods and writes the pod manifests. Karpenter evaluated these pods based on the provisioner constraints. As long as the pod's resource requests fall within the provisioner's defined boundaries, Karpenter will find the best match for the request, considering Kubernetes, defined labels, and scheduling constraints. If the constraints make it impossible to find a suitable match, the pod remains unscheduled. Karpenter supports various Kubernetes features for scheduling pods, including node affinity, node selector, disruption budgets, topology spread constraints, interpod affinity, and anti-affinity. By leveraging these features, Karpenter ensures efficient and optimal resource allocation, enhancing the overall performance and stability of the Kubernetes cluster. If you run Windows containers on Amazon EKS, you might find the latest update from AWS intriguing. Karpenter now supports Windows containers. And now developers can seamlessly manage and scale their diverse workloads on EKS with ease. By offering a unified autoscaling solution for a wide range of workloads, Karpenter empowers users to accelerate innovation, streamline experimentation, and ensure a highly available application infrastructure. Thank you for joining me, and happy scaling!